Galaxies. If I want you to picture what you think of when you think of galaxies, and if you're someone who doesn't work on them for a living, or maybe even if you are, you'll probably picture something like this: one of these beautiful spiral galaxies that's a lot like our own Milky Way. And we see a lot of these around us nearby in our universe. There's also a lot of galaxies that look like this. This is an older elliptical galaxy. We call it red and dead. It's either literally run out of gas to form new stars, or maybe the gas has warmed up and it's too hot and it can't cool down to form new stars. But either way, it looks very different from the spiral galaxies. And most of the big, bright galaxies we see around us will look like these. But if we go back in time, and you might recall that Hubble is a time machine. As we look back at these distant galaxies, we're seeing them as they were billions of years ago because the light took that long to reach us. And so as we fly through this ultra deep field image, we're seeing more irregular galaxies. They've yet to form these beautiful spiral or elliptical structures. And so here's a slide that our outreach department put together, showing a flipbook of galaxies through time, the spiral galaxies nearby, and then more irregular galaxies that have yet to form these structures in the earlier universe. In addition to blank fields, we've also used gravitational lensing to magnify the distant universe. This is an image from the Hubble Frontier Fields program. And to remind you how lensing works, there's a mass from, say, a massive galaxy cluster that bends space-time, the mass of the galaxies themselves, plus a lot of dark matter. And light follows that curvature in space-time to us. We see multiple images of these distant galaxies, and we see them magnified, so we're able to study them in more detail. If you put this galaxy cluster in front of a deep field, then, or in front of distant galaxies, you'll see them brighter than you would otherwise. And so we've been doing this for a long time, both with Hubble, and we'll continue to do this with JWST. So here you see the ultra deep field, and again, one of those frontier fields clusters. And they have yielded many discoveries, including some of the most distant galaxies known. So these here are the two most distant galaxies known, at a redshift of 11. On the left, Pascal Osh's most distant galaxy, and mine on the left, on the right. Mine is lensed by this galaxy cluster, and you actually see three lensed images of it. And the brightest image there is about the same brightness as Pascal's galaxy there. So these are both relative. They're very faint, but they're 26th magnitude. They're bright enough that we can study them in more detail with JWST, and we will in cycle 1. So we're looking back 97% of the way to the Big Bang already with Hubble, 13.4 billion years ago. And there's still 400 million years that's yet unseen. Webb will push further back and enable us to see some of those first objects. We've yet to see a single object that formed in that first 3% of cosmic time. And when I pitched this to Ray Villard, we were doing a training how to talk to the media, and he said, well, that's some people might find that impressive, but it might not be the best way of presenting it, because we've already gone 97% of the way back. So, what's a few more ticks to 98 or 99%? I think it's exciting, of course, but, he makes a good point. So I think one of the other things to emphasize is that when we see these distant galaxies, we can't really see them that well yet with Hubble. So as Carl Sagan would say, look again at that dot. And that's what we're going to do with Webb in cycle 1 and beyond. Of course, Carl Sagan probably would have been most interested in all of the exoplanet observations, to be upcoming with Webb. And you could say this about the exoplanets too. We're going to look again at those dots. These distant galaxies we can barely make out, with Hubble. And what do we know about them so far? Well, we know we don't know a whole lot, but we know that they're very small. this very distant galaxy is about 1% the size of a galaxy like our Milky Way. So maybe 100 parsecs across compared to, kiloparsecs. Um, and so but it might look more like this when we actually get a better image of it. This is a dwarf galaxy nearby. And you can see in this animation below that this is probably the history of a distant galaxy like this. There were many mergers that took place. There's a lot going on. So, again, we probably won't see a beautiful spiral galaxy like this. We'll probably see something, very active and still forming. But some simulations do show some spiral structures in early galaxies, at least some of the time. So it's going to be very interesting to see, what this galaxy looked like, and if it's very active, or if maybe there's some sort of passive quiescent phase that we might see. You notice this dwarf galaxy you see at the top right. It's almost so small that it's nearly blowing itself apart. When massive stars have this radiation pressure, supernovae go off, and they could almost blow the galaxy apart if it's not big enough. And there's a certain size where a galaxy will be able to withstand these explosions. And that's one of the things we're excited to find out with James Webb, if we can see, how big a galaxy has to be, that we'll still see them. We haven't seen that sort of turnover where, we stop seeing galaxies at a certain size. I should say that we're not going to see this distant galaxy quite as well as this beautiful image here, but we are going to see it in a bit better detail. And primarily that's due to the larger primary mirror. Compared to Hubble, which is about 8 foot tall. That's the size. If you're in a normal, if you're in your room, a standard ceiling is about 8 foot tall. So you can imagine that's about the size of the Hubble mirror. Compared to James Webb mirror, it's going to be 22 feet tall. So think more like a 2-story building. So that's we're going to get sharper images and also be able to collect more light and see fainter things. And we'll be able to split that light into spectra, which is very important. And also the other main feature of James Webb is that we're going to higher redshifts. So as you might know, the light is redshifted with the expansion of the universe. And we have pretty much reached the limit of what we can do with Hubble. So with these redshift 11 galaxies, even the ultraviolet light is redshifted to the point where we can only just barely see it with the reddest filters currently available on Hubble. If a galaxy were redshifted just a bit more, we wouldn't see it at all. It would be completely invisible to Hubble. And if I take this wavelength range and I shrink it down for comparison, this is what we're going to be getting with James Webb, just with NIRCam. And then we'll go to redder wavelength still with MIRI. And this will reveal what these distant galaxies really look like. We are just seeing the ultraviolet tip of the iceberg of these distant galaxies. I found this image. This is 20 years old, but it's great. And I admit I had to remind myself what FOC is, the faint object camera on Hubble. That's it's been almost 20 years. It hasn't been on there. Exquisite ultraviolet images you see there at the bottom left. And then WIF-PIC 2 images, Nick Moss. Again, this is an older image, but it shows that in the ultraviolet we only see the hot young stars that emit this very energetic ultraviolet light. And we go to the redder wavelengths, the optical, and then into the infrared, we're getting the full census of what these galaxies look like, including the older stars that are cooler and emit light that's not quite as energetic at these redder wavelengths. So again, we don't expect to see a spiral disk like this, but we don't know. With that distant galaxy I showed you, we might just be seeing that little tip of the iceberg, and we might reveal so much more with James Webb. And so this is what we expect with James Webb from our program, the Cycle 1 observations. You can see that this is a busy plot, but basically with Hubble, we got those gray lines there, and we just barely scratched the surface of ultraviolet light. And then with NearCam, we're going to go to much redder wavelengths, and we're going to be able to distinguish uh, between different models that show basically how old the galaxy is. Again, we expect it to be very active and have a lot of young stars, but it might be older. There might be an older population of stars there, and we'll be able to distinguish that, how much dust there is, just from the imaging alone. And just to give you an idea, we don't know when these observations are going to be scheduled yet, but for this, yeah, in general, for James Webb, we might hope for summer of 2022 observations to start. For this particular target, we're looking at November as the earliest possible. So it might be a year from now that we're starting to get new imaging of this galaxy. So very exciting. And I've made all the data public immediately for my programs that I'm leading. So anyone will be able to look at this as soon as it comes in. And I show my collaborators on the right there with the great, thanks to all their contributions. Certainly couldn't have done it without them. And even more exciting is the spectroscopy. So we don't have this capability currently. We'll be able to take these distant galaxies, spread out the light, and I've illustrated here what we might expect for galaxies nearby at redshift 0 to progressively higher redshifts, including redshift 11 here. The main feature that I want to emphasize is that there's the gas was more pristine in the early universe. In the very beginning, there was just hydrogen and helium, and then it took massive stars and supernovae. It created these heavier elements. So all the star stuff that we're made of, and the heavy elements and a lot of the things around us, that took a while to build up. And so we are, people have studied this, to some degree, and we're going to be able to do that, a lot more with James Webb. And so you see these hydrogen and helium lines might be stronger in these early galaxies. We might see less of the oxygen and neon and things like that. Redshift 11 is a very high redshift. So I'll highlight down here with NearCam what we'll be observing. NearCam and NearSpec will be observing in cycle 1, and we're just going to get these lines right here. And then in cycle 2, we're going to see what we see, and then we'll propose to get some more of these lines to learn more about it with MIRI. And that was an illustration, and this is more what the data might actually look like. This is a simulated spectrum, actually from the ETC Pandea, showing what we might see. And remember, we see 3 lensed images, so we'll get a spectrum for each. We'll be able to stack them. And so again, we might get a few lines here, but we'll already be able to learn things about the star formation rate, the metallicity, like I mentioned, how strong of an ionizer this galaxy might be, and things like that. So that's a little bit about this one program I'm leading. Of course, there are many other galaxies that are going to be observed by James Webb, and I made this compilation of strongly lensed galaxies that I could find. Apologies if I missed any, but this is obviously very exciting that we're going to be able to see all these details in these strongly lensed galaxies. And I also redid this same figure. I put all the galaxies to scale, and so now you can see. So this is the size. You'll see all of these on the sky. This redshift 11 galaxy, very small. And then some of these other galaxies are lensed and magnified to be much bigger, so that we're able to see these internal details. The sunburst arc is a fantastic, very strongly lensed arc, and you see all these tiny clumps in it with Hubble already, and with James Webb we'll get, exquisite detail from imaging and spectroscopy from that program. I also want to highlight this galaxy here that came from our Hubble survey relics, which I've called the Sunrise Arc. And my student, Brian Welch, who's currently on the job market, he's been doing fantastic work analyzing this lensed galaxy. He has a paper submitted to Nature that we expect to be out hopefully in February. And this is the most highly magnified galaxy in the first billion years, and we're going to be observing it also in cycle one. And just some of the science we expect. Brian has done a really great job modeling this galaxy, so doing the lens modeling and reconstructing what it might look like when it's de-lensed. And he's identified 7 different small features in this galaxy, and out to 5, and on scales of like several parsecs. They're very small features. And then out to about 500 parsecs in radius. And I think we'll be able to put slits on all of those little clumps and get spectra of them with near spec. And so we'll be able to measure things like gradients across the galaxy. And so we might find that this core, what we think is the core, is maybe older. Maybe it has more metallicity. It's more enriched than these outer clumps. Or we might find the opposite. That's been found in some distant galaxies, since the galaxy hasn't fully formed and maybe more enriched things are still falling in. So very exciting to have this exquisite level of detail in such a distant galaxy in the first billion years. And here's an idea of what that spectrum might look like. The redshift 6, we see a few more lines already with near spec than we could at redshift 11. And if that's not exciting enough to see these parsec level details, with JWST we could also study the first stars individually. So there have been, just in the past few years, this is a new field of study with Hubble, from the Hubble Frontier Fields program. There have been 3 individual stars that have been discovered at redshift 1, 1.5, magnified by gravitational lensing by factors of hundreds or even thousands. And we have another discovery that my student Brian Welch made, even more distant star that isn't out yet. But we're very much looking forward to that, and we're going to observe it with JWST. And so we will be able to study the first stars with JWST. Few had dared to dream that, really. We had talked about observing the first stars with JWST, and we mostly thought that would be sort of integrated starlight from the first generations of galaxies. But just recently, within the past few years, we found that when we get lucky, we're able to see these individual stars and study them in the distant universe. And they might be very massive stars. They might have low metallicity, not so enriched. And I understand there aren't even that many like that locally nearby that are known. So it's a rare opportunity. It could be to study massive stars like this and learn more about them. I'll just end with my kid again, who he wanted to be a witch for Halloween, but when he knew I was dressing up as James Webb, and he thought, Daddy, I want to be a star that you can observe with James Webb. And of course, he has the star there. And I thought, I normally look at galaxies with James Webb, but I think we're going to get our wish. We're also going to be able to observe young stars in the early universe with James Webb. And that's all I had. I wanted to help advertise the rest of the talks. I'm really looking forward to seeing these myself. And thanks again for organizing, and thanks everyone for tuning in. Happy to take questions.
All right. Thank you so much, Dan. It's very exciting. So as before, please type your questions in the chat, and I'll read them. So while we wait for that, I did have a question for you. So you talked a lot about going for the very earliest galaxies with NIRCam, and you talked a little bit about MIRI, but not so much. So I was kind of curious. Of course, MIRI is a bit less sensitive than NIRCam, but it will trace different things, and so I was kind of curious how far can you go with MIRI in this context?
Yeah, absolutely. I mean, maybe it helps to bring up this slide here. These emission lines are very exciting to study in distant galaxies. So at redshift 6, we can do this with near spec. At redshift 11, we're going to need MIRI to do this. And it will be possible. I mean, I looked into it for the redshift 11 galaxy. I almost, included that in the proposal. My colleagues sort of talked me down. It would have been a much a larger proposal. And I think, we're going to be better off seeing how much flux there is before proposing with MIRI. But the point is that H alpha is sort of the standard line to measure the star formation rate very precisely. Oxygen 3 has been seen in very energetic galaxies with high star formation rate. It's a sign that this galaxy has very strong emission, highly ionizing flux. So we're going to be able to, to get those lines and a host of others, just depending on how deep we go. We're fortunate that these galaxies are lensed brightly enough to do that, even out to redshift 11. And these might be some of the best targets for the rest of JWST's lifetime, since these are the brightest ones we found in all this time with Hubble. And yeah, but there'll be plenty of more galaxies that at lower redshifts, that MIRI will also be able to pick up a lot of these lines. So yeah, there'll be a lot to do with MIRI too.
All right, thanks. I also wanted to note that I think these observations of individual stars at high redshift they're just it's just crazy. Uh, I wonder if you could say maybe a few more words about what kind of stars these are, and with your JWST observations, are you able to observe? Do you think there's a chance to observe a wider range of individual stars at high redshift, or will it be the same ones?
So we will try to find more stars like this. We've been very lucky with these. But in order to find more stars like this, we're going to need to observe galaxy clusters repeatedly over the years. And one of the ways we find them is they vary in brightness. So they aren't, these, I should say, these, I'm not talking about supernovae. That's one way that we see individual stars that are very distant. And that's also very interesting and exciting. These are unexploded stars individually that we're able to see just because of these very high magnifications. But they do fluctuate in brightness due to microlensing from the galaxy cluster. And so if we observe enough of these galaxies repeatedly, then we'll be able to find more of these stars. We may be able to do that ourselves through regular geo proposals, or we may need some help from the director to be able to do that. And with this star that we have time for, we will be able to, in cycle 1, we'll be able to put it on the HR diagram. We'll be able to constrain its luminosity and its temperature, and begin to, and confirm it's a star, and to be able to say some things about it. Once we do that, we can come back in future cycles and get more data on it. We think that the flux of that one is very stable. We'll be able to do that kind of thing. And yeah, I mean, the more that we're able to find, the more that we'll be able to, study. If we have, more of a large population, we can get to these early stars, the better, obviously. So yeah, it's very exciting.
All right, thanks. So we do have one question in the chat here. What is the metallicity of your redshift of 11 galaxy, and what do you expect for the redshift of 13 galaxy?
Right. Yeah. So we don't know. I'm very excited to find out. I mean, I showed this. I should say, these are just guesses. So this is meant to be solar metallicity. Galaxies have a wide range of metallicities, but I just did this to illustrate as metallicity decreases, how the spectrum might change. And we don't have metallicity measurements at such high redshifts. It gets tricky. I'm not an expert in this, so I've had people explain it to me, and they said it's very hard measuring metallicities. For one thing, the different lines that you might use to measure a metallicity, they change with redshift, because your telescope will measure a certain wavelength range, and if a galaxy is at a different redshift, you're going to need different lines that pop into that observable range, and it's challenging to say the least. So we don't have those metallicity measurements just yet, but yeah, it's gonna be very interesting. There's obviously predictions from simulations. The most exciting thing we might hope to find is a completely pristine galaxy made of population 3 stars. So stars that are just made of hydrogen and helium, and you wouldn't see any other heavy elements, no oxygen or neon or anything. We don't really expect to see that. We expect things to have enriched fairly quickly, but we're going to look and find out. These population 3 stars have been theorized, but never directly observed. So yeah, lots of exciting possibilities.
Right, yeah. Scott says it looks like you could get oxygen over hydrogen. I also note that just for the folks on Facebook, that metallicity is the amount of stuff that isn't hydrogen or helium.
Right.
All right. I think that's all the questions we have. So thank you so much again, Dan. This is really exciting.